It's a cool problem. Yeah, it's one to me that feels polynomial time. It feels like you should be able to do something better, but maybe. I think out of the problems I know that are NP complete, or co-NP complete in this case, that's the one that I think has the best chance of getting got as being polynomial time. But a lot of people have worked on that problem. So, okay. Hey everyone. Hey everyone. Welcome. So today we're going to do another reduction. We're going to start with a bit of recap. And then we're going to do the proof of Vertex cover, and then we're going to do another proof today. All of this right here should be recap. We'll talk about it in a second. But before that, administrative stuff. Number 1, Project 3 is released. You thought I forgot? No, it's still happening. But this is going to be due next Wednesday, the entire thing. And in compensation for that, two things. 1, it is only the coding part, so you don't need to do the written part for this one. You've gotten tested on written a lot. For this one, I just want you to write an efficient algorithm to do the problem. Don't just LLM it. It's bad for you. But do try the problem. It's seam carving, like I mentioned. You're going to. It's a pretty fun one, honestly. It's a pretty fun one, and this should be substantially easier than the other problems that you've done so far in class. So a little bit of lighter load towards the end here. Second thing that I'm willing to offer related to this is the surveys have just been released, the surveys for all of you guys, the SCRIs. I really like getting feedback, whether it be good or bad. It's helpful for me. This is my first time teaching this class. This is an experimental way to teach this class, so I am very interested in getting feedback from all of you. In particular, if 85 of the students in this class, there's enough missing that some of them are not going to hear this from me right now. If 85 of you complete the surveys, I will drop your lowest homework of the projects. Okay? That is the last time I'm going to mention it. I will update you on the stats if you need to know them. But good luck. Good luck. I don't know if it'll happen. It has happened in my previous classes actually, but it is unlikely to happen in general. So please do. 90. Yeah. I don't think you can. Okay. I will also say with the reviews. Hey. Quiet down, Karsh. I'll say with the reviews. I really do want honest feedback from you all on this class. Whether you like it or not, whether you like me or not, I just like to know what worked and what didn't. It's important for me. I want to be a teacher, or I am a teacher, I guess. I want to continue being a teacher, and I want to keep improving. Cool. All right, sounds good. All right, so let's start with some definitions, a little bit of recap. So we had this diagram that we started talking about. This is how we started to group the difficulty of problems. We had a couple different views. This is the concentric circle one, which gives the intuition that some classes are inside of others. For example, we have this class P, and is entirely encircled by the class X time, which is problems that are solvable in exponential time and problems that are solvable in polynomial time. We know that there is some how do you say that? They're concentric. They're concentric in that this is entirely a subset of this. So we also saw these two other classes, which are a little bit more interesting in the focus of our lectures, which is NP and co-NP. Can someone remind me what the class NP is? Yeah. Exactly. We have the definition over here. So all the definitions are written here. If you can't quite see them, I'd recommend at some point you come take a picture of them or something. I'll leave them here for you to write down in your own time. If a problem is in NP, then giving some certificate, which is any sort of information, this is a very broad thing. Generally, what we'll see in this class and in real life is that the certificate is going to be a solution to the problem. So you'll normally see, but it can be other things. So hypothetically, you could come up with a clever way to not give the solution and give something else. But generally, it will be the solution. And given that certificate, A may be verified in polynomial time. What this means is that it is possible for us to prove that it is true if it's true in polynomial time. So, for example, a problem like SAT, A problem where we have, so 3-sat is an important problem to us. We've talked about it several times. As a refresher, it is groups of clauses which are 3 variables all ORed together. So something like x1 or x2 or x3, and then ANDed with other clauses. So something like, say, not x2, so I have repeat variables that can be negated, or x1, it can be repeated, or whatever, x10. It can be any of these. Let's say not x10. It can be any of these, and we'll have n of these clauses. Okay? And this is a problem 3-sat. And 3-sat, you'll notice, if I wanted to verify it, then I could give a solution. I can give an assignment to all these variables, and that would allow me to say, yes, this is a satisfiable problem. There exists some assignment of these variables that will resolve to true, which is the goal of the 3-sat problem. So if I were to give the assignment, I say x1 is true, x2 is false, etc., 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 I'm able to just loop through the clauses, make sure each one of them has one true statement, and then if all of them do, I say, good, I have verified that this is correct. But there's the other class, co-NP. Can someone remind me what is the difference between NP and co-NP? Yes?
The NP problem you can confirm with yes in non-deterministic confirmation that will terminate the inverse.
Yes, so where NP is the problems that I can verify, that is, I can give a yes answer to in polynomial time if given a certificate. Co-NP are problems that I can return a no correctly in polynomial time given a certificate. So you may notice, you could say, okay, why are these different at all? Well, let's look at the SAT problem. So in SAT, if I'm given a solution, very easy to confirm a yes. What information should I be given so that I confirm that there is no way to satisfy this? A lot trickier, huh? Okay, yeah. Which one of the clauses is false given what assignment? A contradiction. Well, you need a proof. You need that a proof of contradiction is your certificate, and we don't know if one exists. We don't know if it's possible to do that in polynomial time. Well, there would be a proof, but there wouldn't necessarily be one that runs in polynomial time. So, yeah?
Is there a restriction on the size of the certificate?
It will have to be polynomially sized because I have to read it. Yeah, there's not a specific restriction to it. It's just that I have to use it in polynomial time. Exactly, exactly. I can't give all of them and just say, it's stored in some way where I can retrieve them in polynomial time. You can't do that. Okay. So, it is possible that there exists some way to do this. We don't know if co-NP and NP are different sets, actually. We don't know if they're equal or not. But it at least is a lot more difficult to reason it out. It's a lot more difficult for us to see that this is negatable or falsifiable in polynomial time. Okay, so that's the distinction between these two classes. All right, so then we developed a bit of a tool called a reduction. So a reduction, can someone tell me what the point of a reduction is? Yeah. Yeah. So that's how one operates. The point of one is that it allows me to say that one problem is harder than another. Okay, so the reason that we use this less than equal to sign is I'm trying to say that this problem, the uppercase in this class, by the way, will represent a problem, and lowercase is going to represent an instance of a problem, just for the record. So when I'm doing a reduction, I'm trying to show that one problem is harder than the other. The way that I go about doing it is I take any arbitrary instance of that first problem, the problem that I'm reducing from, we'll say. So in this case, A. I take some instance of A, or every instance of A. I convert it into an instance of B using some polynomial time function. And it's important that it's polynomial time, otherwise we can do things like up here where I can just solve the problem if I don't restrict it to polynomial time. And then for every, I'm using E here, by the way, as encodings of inputs. This is a common verbiage for when I'm talking about instances of a problem. Say I have some encoding of the problem A, and then the truth value of that A problem on the instance, for every one of these instances, is going to be equal to the truth value of my second problem, B, which I'm reducing to. after I convert it using my function. Okay? To give a specific example, what we did previously is we showed that 3-sat was able to reduce to independent set. If you remember this, independent set. And the way we did this is we created for any input, I'll use that same instance of 3-sat just to save myself some drawing. But if we take some instance, what I can do is I can take each clause, create a little click of each one of the variables, and I'll label them for myself, x1, x2, and x3 in this case. And I connect each one of them. Okay? And this is this restriction here by the definition of independent set, which is I want to find a subset of nodes from some graph such that none of them share an edge. And I want to find some independent set of size k. So this is of size k, I should say. Size k. So this is restricting it so that I can only choose one of these variables. And then the other restriction is if I keep going through all the clauses, then if I have x2, x1 bar, I wrote them in a weird order, that's fine, and then x10 bar, whatever. What I do for each one of these clauses is if I have negations of terms, so if I have x1 and not x1, I don't want them to both be able to be chosen, so what I can do is I can connect them to each other in my graph. Now if I try to find an independent set, I can't choose both this and this. And what we're going to end up doing is we're going to say that the independent set that we generate from an independent set solution on this new graph I've created is going to give us the truth value of the 3-sat on the original problem. So if it's possible for us to assign one variable to each one of these, in the conversion we're going to choose k is equal to n, so each one of the clauses has to have at least one true term in it. And we're going to choose each one of these, and then if this is possible to construct an independent set of size k, which is n, the number of clauses, then I know that it's possible for us to find a satisfying assignment for each one of these clauses. It's exactly the terms I chose in my independent subset. Any term I didn't choose one way or the other is free to be chosen however. It doesn't matter. Okay? Does this roughly make sense? I'm just overviewing it. I'm not doing the full proof again. You'll notice that in the definition of reduction, which I'll draw your attention to again, when we're doing the reduction from A to B, which is the verbiage, I'm reducing A to B. I'm just going to repeat it because people usually mess this up. I need to show that every true instance of A implies a true instance of B, or it implies an output that is true of B, and vice versa. So I need to prove both of those things. We'll do an example of this later in class, but something to keep track of. That's one of the main difficult problems of reduction. So it isn't just how do I construct it, although that is the artistic, difficult, conceptual part. I also need to prove that if I have a true 3-sat, in this case, if some instance of 3-sat is true, then the corresponding independent set will be true, and vice versa. We'll see an example of how to do this proof later. That's reductions. We'll do another one later in class, or we'll do probably 2 more in class, so you'll get some example. And then we have the resulting effect of having a tool like this. Firstly is NP hardness. So we say that a problem is NP hard if for every problem in NP, that is, I'm using I here as some arbitrary problem, there's a reduction from I to the problem A that I'm claiming is NP hard. Okay? So what this corresponds to is saying it's everything that is outside of this NP circle outward. Okay? So that's the idea of NP hardness. Is it's everything that is as hard or harder than every problem in NP. Cool? Cool. And this does end up being transitive because we're doing a polynomial time translation from one problem to another. If I chain those, a polynomial of a polynomial is a polynomial, so I can have some new, more complicated function that converts between them. You understand? So if I'm saying A reduces to, if I say A reduces in polynomial time to B, which reduces in polynomial time to C, and I say that there's some function f that converts A to B, and some function g that converts B to C, then I can say that there exists the reduction A to C using the function GF, G compose onto F with whatever the input is. Understand? So we can also say that they chain together. And we know that this function is also going to be in polynomial time if both of these are. Yes?
Does NP hard have to be
NP hard does not need to be an NP. So in fact, everything in exponential time is NP hard, and beyond that is also NP hard. It's a general definition. It's not part of the concentric view. It is everything above NP hard. Okay, so everything but like outside of NP hard. The thing that is inside of NP is NP complete. So we say that a problem is NP complete if it is both NP hard and it is inside of NP. So they're not disjoint. They have some overlap. We know this overlap exists. So we need to, if we want to prove that something is NP complete, we need to prove both that it is NP hard and that it is NP complete. Okay? If both of, or not NP hard and that it's in NP, and that would mean that it's NP complete. Sorry for this, but cool. Yes. So NP hard is, yeah, for every problem in NP, you have to show a reduction exists. Very cleverly. So this was the proof for circuit sat being NP hard that we did in the previous class. So circuit sat is our primary, or it's our original NP complete problem. Circuit sat is just an arbitrary circuit. So instead of it being in CNF form, it can just have ands, nots, and ors in whatever way. And we need to know whether or not it is satisfiable, whether or not there's a satisfying assignment. So it's clearly a more difficult problem than this one, or it's a more broad problem than this one. And what we find is that every program that can run in polynomial time can be converted into a circuit in polynomial time and then can be solved. So what we find is that every one of these problems, essentially, I'm not going to go into the nitty-gritty of the proof. If you'd like to, you can look it up. We can convert every one of these problems into a circuit sat problem. And we show that by making a general claim just about programs in general. So we can claim that every program can be converted into a circuit, and then circuit sat then captures everything. It's a very clever proof, but it's a little involved, so I'm skipping over it. If you'd like to, you can look it up online. Okay. Yes?
so NP complete?
They are, yes, essentially. So the NP complete problems are the hardest of the NP set. Yeah, that's fair to say. I will remind you all that hardness here is a very specific thing. It is, I'm able to solve I'm able to solve problem A using the solver for problem B, given that I convert it in some polynomial time. This doesn't mean that in practice it's a harder problem. It doesn't even mean that you should expect to have higher runtime, or even that the bounds on the runtime are lower. There can be some problems where we have asymptotic bounds that are tight that are worse on these, although none of the problems in NP have tight asymptotic bounds. So, yes? I'll draw your attention to this in a reduction, less than and equal to, right? And there's a reason that we use that symbol, that it's not just less than. It's possible for problems to be equally hard. So what we show is that there's some problem in NP where any one of these problems, I can convert it to that problem, meaning it must be the hardest, but it still can exist in NP. Make sense? Yeah. And if you're worried about itself, how can it be harder than itself? It can be equal to itself. With the function to transform is just nothing. Okay? Okay. Yeah.
In that definition,
So the definition of NP hard doesn't reference any B. I assume you're saying.
the one above, sorry.
Yeah. So in the problem above, the reason that we care about B being NP hard or A being NP hard is what we actually care about, is because if I have A as NP hard and I can polynomially time reduce it to problem B, then what can we say about B? It's also NP hard. So the reason that we do this reduction, where we go from a known NP complete problem like 3-sat, and we do a reduction to the problem independent set, is because now if I do this reduction, I know that independent set is also NP hard. And then the only remaining thing for me to know if independent set is NP complete is to figure out if it's in NP. Which again, with independent set is relatively easy. We just look at some assignment of the set, and if it works, then great. Okay? Any other questions? Okay. So now let's look at the problem from last quiz. So a few of you did notice, and Tomas, thank you for the note here. I did actually missay the vertex cover problem, so we're going to restate it, and then we're going to do the proof again. We're going to do it more thoroughly this time. So the problem goes like so. So what we want to do is we have this problem, vertex cover, and what vertex cover is going to be is given some graph, and we're going to be expanding our chain here to vertex cover. And the way that vertex cover is going to work is we are going to be given so an instance of vertex cover is going to be both a graph, which is going to be vertices and edges. This is just common notation for being given a graph. And it's going to be some objective k. I guess I'll remove that this is k. We'll just use k for vertex cover. So we're going to be given some graph and some number k. And we'd like to know, does there exist some subset? Does there exist some subset of V, which I'll just use as S, some subset of V, such that every edge, for every edge, I'll call them AB. So the edges in A, B. For every one of these, either A is in S or B is in S. Okay? So what this means, not logically, is if I have some graph like so, something like this, then I'd like to choose some subset of nodes, let's say this one, and let's say I choose this one, right? And I'd like it so that every edge has one endpoint, either one of its endpoints in S, one way or the other. Okay? So does this example work? No, it does not, because this edge right here is not covered by either of them. Okay? So my problem in the previous class, I said it was covering vertices is actually covering edges. So that's a mistake I made. Is there, though, a subset of size 2 that would vertex cover this? Yes, there is. It's going to be these two. Okay? Cool. So now we want to do this reduction. Okay? So firstly, I'll ask, is this problem in NP? Yes, it is. It's relatively easy to see this. Once again, we're going to see this for almost all the problems we talked about in class. We can just get the solution. I can give you the solution. You say, "Yep, it's doable," and that's all we need. We don't need anything else. But how do we do the conversion? What's the relationship between independent set and vertex cover? Could someone tell me? How can we translate from independent set to vertex cover? So remember, we need to find some polynomial time function such that for every possible input of the independent set, we can convert the problem into a vertex cover problem such that the truth value is the same. So that is, if I have some independent set problem, I should be able to convert that into a vertex cover problem, and if this one was true, then this one will be true, and if this one was false, this one will be false. Okay? So how do we do this conversion? Anyone want to share? Sure. So as a reminder of the direction of this reduction, so we're doing independent set, we're converting an independent set into a vertex cover. So if we're doing this, then I have some problem here, right? Let's choose this number as j. So this is saying set of size j exists. Set of size j where none of them share an edge. Okay, so I want to know if I have that, how can I convert that into a vertex cover problem? So let's say I have this graph, and I want to know does there exist an independent set with a size j? So this is I'll just say I want to know this on this graph with the number j, right? So I want to know, is that true? How could I convert this into an instance of a problem of vertex cover? Yeah.
Number of edges minus k.
Not quite. Not quite. Yeah. Exactly. So this will become the new vertex problem. All we're going to do when we do this conversion, if I have some number j here, it turns out that if I have some independent set, let's say these two, right? You'll all agree those are an independent set. It turns out that if I look at all of the nodes that are not in that independent set, they will form a vertex cover. So in red here we have the vertex cover, and in blue we have the independent set. And you'll notice they happen to be the same number, but that need not be the case. You can imagine I add some other node here, and this would mean that now I could have an independent set of size 3, and I only need 2 for my vertex cover. Okay, does that make sense? So the conversion is actually very simple. Instead of like what we're going to do as our function, I'll write it as using our function notation from there. I say if I have my instance of the problem, which is g, and the number j, then this is going to convert it into an instance of this problem where it is the same graph, but the number is now just the number of nodes minus j. Okay? Make sense? So now that we've come up with this scheme, here are the problems. And this is a very simple conversion overall, but there could be more complicated ones. And there are often more complicated ones. But if we have a simple one like this, right, then what remains to us? What else do we need to do to be able to prove that vertex cover is NP complete, or that this reduction works? What do we need to show still? So I've shown now a strategy. I've shown that this function, and I've said that it exists, and I've argued some intuition. But what do I still need to prove? Exactly, I need to show a few things. So one is I need to show that f is in polynomial time. It's pretty easy to see, just doing a subtraction is in fact in polynomial time, but it is something that we need to prove in general. We'll see later on in class, it is not always that easy to prove. But good, nice. What else? Yeah? Exactly, so we need to show that every instance that gives us a true value for independent set must also give us a true value, that is a one-way implication here, to vertex cover on our converted problem. Okay? Well, and what else? There we go.
That's what I.
Okay. There's one more. Yes? Exactly, the opposite direction. So here you'll notice it is an if and only if, which we write, by the way, also as IFF, because you didn't see that notation before. If and only if, meaning we need an implication both ways. It's difficult to prove them simultaneously. It's easier to prove them one at a time, generally. So we're going to say also that for all of these, we can say that when it is not true, or I'll do the conversion the other way first, and I'll show you that there's an equivalent. So if I have a vertex cover FE, then it must also give us that the independent set was true. So if I say true, then it has to be true in the original problem, and if the original problem is true, then I also have to say true. That is the same as having this two-way implication, or if and only if. Alternatively, by the way, we can also prove here instead that a not on the original problem, so not true on the original problem, implies not true on our vertex cover also. There's an equivalent statement. Logically, these two things are equivalent, so you can choose either one of them. Same goes for this. If it's easier to prove negative cases, then you can choose those, or you can do the positive cases. So let's do this for this problem, this reduction. First off, F is in P, that's very easy. We've already done that. Cool. How about this reduction? How about this implication, sorry. If I have a true on the independent set, then how do I know that that's going to be a true here? I need to prove that it gives me a true there. Give you a second to think about this one. See if you can come up with a quick proof. All of these proofs are relatively straightforward. Okay. Yeah. All that f is doing is changing the number j to count of v minus j. That's a very easy operation. It is in fact constant time, or log n if you really want to argue. Yeah. It's saying the truth of the entire problem. So as a reminder what's going on here, it's saying that the independent set problem, which asks, given a graph, does there exist an independent set of size j? It's saying if that is true, I want to convert it into a version of the vertex cover problem that is only true if this was true. Where vertex cover is, does there exist a subset of nodes of size k such that all of the edges have one endpoint in that subset? Okay. Yeah.
We were also given the option that we wanted to prove that these not the larger ones apply.
Yeah, exactly. Yeah, so you need to prove both implications, but you can do it through negation or through the positive. You can say that yes implies yes and no implies no, or you can say that you can do the reverse. Yeah.
I was confused for a second about why would that be called P, but
Yeah. Hmm? Okay, so you'd like to give your guess? Yep. Exactly. So, by the definition of independent set, none of the nodes in the independent set have an edge between them. So if I consider the edge between them, none of these exist. Therefore, if I take the reverse, then there's either edges that have one endpoint in the independent set and one in not the independent set, s or v minus s, if you'd like. So every one of the edges has to have one endpoint, either between two of these nodes or between one of these nodes and one of the original subset. There cannot exist any here. So if I choose the inverse, all of the nodes that are not in the independent subset, every single edge must be connected to one of them. Does that make sense? Okay, so that's this proof here. I'm not writing it all out, but that would be the heart of the proof. And then the other case. So now the other case is if I have the vertex cover is true, then how can I use that to imply that the independent set is true? Or if you prefer, if I do not have an independent set of size j, how could that imply that I do not have a vertex cover of size v minus k, or j in this case? Accept that also. Okay, anyone want to share? Yeah.
Not an independent set, then there must be our independent set.
It must mean that there is no subset of size j where two nodes don't share an edge.
Yeah.
This is a true statement. This is a true statement, but it is a little bit finicky. You are basically negating negation. So you'll realize probably that the other version is easier in this case. It's not always the case. You have to choose based on the problem. What you said is correct, but there is a simpler way to say it. Yes?
If we're able to
Exactly. So if I look at my vertex cover, by the definition of a successful vertex cover, then I know that every edge has one endpoint in the vertex cover. So if I take the inverse of it, I know that there must be no edges that are between the two that I haven't seen, because I know that every one of these edges has to be connected to one of the vertex cover edges. So if I invert it, then none will exist between things that are inverted because of this. They're essentially, because these problems are so related, these are essentially the same. You may notice they're just very slightly tweaked from each other, but yes, this is essentially it. And so from these things, we now have these three things combined have given us this reduction. The independent set reduces to vertex cover, and then the fact that vertex cover is in NP, which was almost trivial to prove, then vertex cover is in fact NP complete. Cool. Yes?
Why so F inverses them?
What F is doing is just changing the instance of the problem, the input to the problem. So all it's doing is replacing J with V minus J. That's all it's doing, is what F is doing. What we are arguing then is that those two things are, like, this will give us this relationship where true implies true and false implies false. The heavy lifting is on us to prove, not in the actual conversion. The actual conversion is very simple here. Yes?
I don't know if I missed this, but for these
No, we can't. I believe that doesn't break the problem if for this version. But the previous version that I talked about, where I said it was covering vertices, does break it. But with covering edges, it doesn't, I believe. If you come up with a counterexample, please talk to me. But I'm pretty sure it doesn't break it. These are very famous problems. I just misspoke it last time. Yes.
So when we're if you just
Usually you should give a little bit more than that. Like, for example, SAT. I can say, given a solution, I can iterate through each clause, make sure each one is true. So something like that. You can't, I mean, there's probably a way to always do it given a solution, but sometimes it's easier to do other things. For this class, again, though, generally it will be just given a solution. It's generally easier for these problems. Yeah? Maximal independent, so it could, yeah?
what if I just had like a single
Then it would have no vertex, or it would have no edges, so the vertex cover would be no nodes. Yeah, that's fine. Yeah. Yes. So I'll do it verbally just because it's a lot of writing, and we're gonna have a different proof later in the class. But the definition of vertex cover is that for every edge, which I normally use E for, so excuse that this is instance or encoding, but for every edge in the graph, every single one of those edges has either has one of its two endpoints in this subset S, let's say, of the vertex cover. Right? If I want to call the vertex cover, I'll write it a little bit here. So I say for every edge, I'm going to write I'll write E again. Sorry, it's a different E. Try not to be upset about that. For every E, which is an edge from A to B, I have that one of these, either A is in S or B is in S, where S, the size of S, is equal to J. Make sense? So this is the definition of vertex cover. Here, I guess I called it K before, but to some variable that I'm given. And I'm choosing that to be V minus J when I'm doing this. So using this definition, I can say that every single edge has to have one endpoint in S, and the definition of independent set is that there are no edges between the nodes that I choose in my subset. And by this definition, there won't be any in V minus S. So if I take all of the nodes and I subtract this subset, or I remove this subset, there cannot be any edges between those. because all of them have one endpoint in S. That make sense? It's slightly less formal. You can do it very, very formally and briefly, but I think the argument is concise enough that it's fine. Okay, yeah?
One question. Sorry. What if out of that graph as my independent set in a single node? I feel like I picked up one left node of the graph and said that's an independent set because there's no edges between
Yeah. So then the entire inverse, so all the rest of them, right, would form a vertex cover.
just not the minimal.
Not the minimal vertex. So this is nothing about minimal or maximal. It's of size, whatever. That's how we converted it into a decision problem. You could rephrase it as the minimum independent set is this size, or the maximum independent set is this size, and the minimum vertex cover is this size. Are equivalent problems, but us choosing a particular value is fine. Was there another hand? That's not one. Yeah.
So basically, that they
Yes, I am saying that. And vice versa, that you have both of them. If there does not exist one, then it does not exist. All right, cool. Are we okay on this? So this is our first sort of full reduction and full proof of NP completeness. Let's do another one. So our next one is going to be a famous problem, a very famous problem that is a little bit trickier to prove. And we're also going to show that it's possible for us to not just chain these together, we have a sort of branch. So we can use whatever one of these we'd like to do a reduction. So in particular, I'm going to introduce a new problem. I'm going to define it over here, just so that I have the definition up whenever we'd like. Sorry if it's a little bit hard to see, but I'll be saying it out loud also, and it'll be all over the rest of everything too. So our new problem is going to be Hamiltonian cycle. Hamiltonian cycle. Anyone know the definition of this? I heard an O. Someone know? Hamiltonian cycle. Okay? I'll call it HC for short other places. Can someone tell me what a Hamiltonian cycle is? Does someone know? Yeah. Exactly. So this is true if for some graph G is just going to be, the only input is, I'll write it here actually, input is going to be a graph, which is just vertices and edges. It's going to be directed also. I'll note that. Directed graph. And we need to know, and we'd like to output, whether or not there exists some path, I guess I should say some cycle, some path in the graph, such that the path visits every node once besides the one that it reattaches to. So it's a cycle, so it has to end back at the same node, but every other node is only visited one time. Okay? So for example, if I had some graph, some arbitrary graph like this, I can have a whole bunch of edges and a whole bunch of stuff going on, like this maybe. And I want to know, does there exist a Hamiltonian cycle? And I can prove that this is an NP by getting an example. I'll give that to you guys for free. If I just choose, like, here's the first one, then here, then here, then here, and then it returns back to 1. So that is, in fact, a Hamiltonian cycle for this graph. Okay? So what we'd like to do is we'd like to do a reduction to Hamiltonian path. Anyone want to give me a guess as to which one we're going to use? Okay. Who thinks it's going to be vertex cover? Who thinks independent set? Who thinks 3-sat? It's 3-sat. So we're actually going to be doing a reduction from 3-sat. This is going to be our new thing, Hamiltonian cycle. I'll just call it Ham cycle. Yeah. And we want to somehow do this conversion. So first off, I've argued very briefly that it's in NP. Does everyone agree that it's in NP? I think if anyone has any issue with that, we can talk about it, but it's pretty easy to see. I can try the path if all the edges exist, and if it doesn't repeat a node, I'm fine. Okay, so now how do I do this conversion? This conversion is a little bit tricky. We can think about what we have. So we're converting a three-set problem into a graph of some sort. What we had previously, we did three-set and independent set. You noticed we did this trick where we turned a clause into some object, right? We turned some clause into a single item here. Some people call these things gadgets. So we have to come up with these gadgets to put together this full conversion. And generally when it comes to doing a reduction from three-sat, we need to figure out what our clause is and how do we constrain them to whatever constraints the other problem has. As a reminder, we're doing a reduction from three-sat to Hamiltonian cycle to show the Hamiltonian cycle is harder than three-sat, so we need to convert any arbitrary 3CNF, that is some circuit with the properties of 3CNF, into a Hamiltonian cycle problem somehow, such that the truth values are equivalent. So how can we do that? Well, let's start with a little bit of things that are generally a good place to start for this. One, we know that we need to visit nodes, right? That's what Hamiltonian cycle is going to be constraining us by. So somehow we probably want each of our clauses to be represented by nodes somehow. And we'd like to visit each one of them and visit them only if their truth value is true. Secondarily, we probably want somehow to have node or nodes representing each variable, one way or another, and we need to constrain it in such a way that if it is true, it cannot also be false. So starting from this point, you can kind of imagine, let's say that there's some node here that's only visited if it's true, then I could perhaps go to the clause and then go back from the clause, something like this, if it's true. So these sorts of things might start to come to you as intuition. I'm giving you a little look into how you might develop the solution rather than just giving it to you. I'm going to give you all just a minute or two to think about the problem and give it a go. This is a hard one, though. It's unlikely that you'll be able to come up with the solution. But I want you to all attempt it. Sure. Yeah, I think people will want it too. Not right now, but I think when it ends, probably this is going to be okay. Yeah, I'm trying to use more board space today. Got it. Okay, I'm going to get you guys off there so we have time for the rest of the proof. Anyone want to give me any ideas? Yeah. Okay. Okay, yeah. What would that mean, fully connected? Not to focals on it. Yeah.
Oh, like
From each, from whatever it's connected to?
inside the clause, yeah.
Okay, yeah. Yes. So we don't want to be able to travel from a node to its inverse, but it turns out we're going to represent these variables as more than just a single node. At least in the way that we're going to do this reduction, which is the only one that I know of. Perhaps there's other good reductions, but this is the only one I know. Anyone else want to give any intuition? It's perfectly fine if you weren't able to solve the problem, by the way. This is a bit of a tricky reduction. This would be, I think, beyond the difficulty that I'd ask of you on the final, just for the record. It requires a little bit of intuition, a little bit of artistry too. Okay, well I'll start saying the solution. I'll go piece by piece, and hopefully we understand. So what we're going to do is we're going to create a chain. We're going to start at some node S. Okay, we call this node S, and we're going to iteratively go through the variables and decide their truth value. So first decision we're going to make is from this node S. We're going to choose either to set x1 to true or to set x1 to false. I'm just labeling these edges, but that's their purpose in here, is either we set it to true or we set it to false. Okay? So now you can imagine if I were to choose to set it to true, right? And I could have directed edges here, like so. I'll explain what I'm doing in a second. If I have directed edges like this, and we say that clause 1 contains x1, right? Then what I can do is I can add two edges, like so. I didn't actually draw this big enough to do the full thing, but I think you'll get the idea. So I can draw it from here, and then back here, okay? So now, if I set x1 to true, my path can go from here, here, go to clause 1, go back, and continue. Okay, you understand? And if I had the reverse, if not x1 was inside of it, then I could reverse these connections. I could say that it goes, it goes here, and then, comes from there. Sorry, it comes from here, and then goes to there. Okay? So now if it's not true, I can take this path. Dun, 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 dun. Okay? But, how could I deal with the fact if this has in it x1 and this has not x1 in it, then what can I do? So what I can do is I can actually increase the number of nodes here. So sorry, I drew it a little bit too small to do the full thing, but let's do it like this. So I have a bunch of nodes now. I think one more. Okay. And I'll redo these. So now, you can imagine this might not x1. So now, if I have not x1 in that, then at some point I'd like to come from x1 up to the clause and then go forward. Okay? And likewise, if this has x1 in it, I'd like to come from somewhere earlier on the left and then go back somewhere further on the right. Okay? So now, by the definition of, I didn't actually put, so one thing I missed on this definition, I didn't write it because I didn't write it super formally. I did. Every node exactly once. It cannot repeatedly visit them. So it can only visit each node once. So if we look at this now, is it possible that we visit C1 and we visit C2? If C1 is just not x1 and C2 is just x1, is it possible that I visit both of them? Is it possible I visit both of them without visiting a different node twice? So again, I'm visiting each node exactly once. I should emphasize that. Every node exactly once. Sorry. Every node exactly once. Just emphasizing it. Exactly once. So if I look at this, right? If I choose to go this direction, right? If I choose to go this direction, then I can go to clause 2 and come back, go here. If I go here and come back, I'd have to continue, right? I can't go backwards. I'd have to repeat one node. So what this is giving us is that if I want to choose, if I want to visit each one only once, I have to choose to either go left to right or right to left. Does that make sense? And because of that, I can only visit nodes that are in the correct cardinality, that are either going forward or going backwards. Does this make sense? Yes?
So what is x1?
x1 is a variable from sat. Remember, we're taking sat, we're converting it. I'm labeling this edge as x1 for the sake of this argument. It doesn't need to be there, but the assignments are going to clauses which contain x1 or contain not x1. Does that make sense? Okay. I'm gonna let that soak in for a second. I'm gonna continue and then I'm gonna review it in a second. Yeah?
Wait, so is like the line of nodes
So far, I haven't finished doing the reduction yet. Yeah, this is just, this line represents x1, and I can either assign it to true or false, and that will determine either it's moving to the left or to the right. Those things are equivalent ideas. Assigning it true is moving from left to right on this line. Then for every other variable, what I'm going to do is I'm going to connect each of these, each endpoints, to a single node, and then I'm going to repeat that same process except with the next variable. So here will be x2, and here will be not x2. Okay? And likewise, if C2, for example, contained not x2 also, right? I'll say that it is x1, I'll write it like this, x1 or not x2, for example. Then on this next layer, it's going to have the same sort of connections going from the right side, then back to the left side, which will be like so. That, and then like that. And I would continue this process for every single one of these nodes, for every single one of these variables. So every variable has one of these sort of gadgets that then tell me which clauses I can pick based on how I assign it. And then the conversion, essentially, if like the way that I could read this as satisfying is that the way that I chose, either going to the left or going to the right, is my assignment of variables. Okay? Make sense, everyone? Yeah?
How do you choose that?
So this is going to be answered by our next question here. So they need to not overlap. So if I have them overlapping, for example, then I no longer have the issue of I can if I have these be exactly shared, then I can just loop through them and then continue. And then either if I choose x1 to be true or false, I'd be able to choose both of the clauses. I'd be able to reach both the clauses, which I don't want. So I need them to be disjoint. So for every clause, I'll need 2 nodes, right? Plus 2 on the end here, and then I also need the start and these middle nodes. That make sense? Okay. Yeah.
If a clause
It can be visited multiple times, except we won't. We say, does there exist a path that does a cycle without visiting any node more than once, or visiting each one exactly once? And it can visit it one time and then not visit it later. That's fine. Yeah. Anything else on this? Yeah. The clauses from the 3-sat. So in this example so far, I would say that my 3-sat CNF is going to be not x1 or some other stuff that I need to define, and x1 or not x2 and perhaps some other stuff. So this here is clause 1. This is clause 2. And I'm saying my gadget here is if I visit clause 1 on the graph here, I visit C1, that means that clause 1 has been satisfied for whatever assignment I'm going through here. That make sense? Yeah.
Since we're doing hand
Yes. Yes. So to finish our construction, because it needs to be a cycle, we'll end up eventually at one of these endpoints, and we'll label it T. So that's after the final variable. We'll connect them, and then that will come back and connect up to S, which is because it needs to be a cycle. Yeah. Okay. Yes.
How does that, like,
So our reduction is then we want to prove those 3 same things as before. I guess I'll call it the 4 things. So firstly, because we want to prove that ham cycle is NP complete. So first off, ham is an NP. We've already proven this. That's fine. Then 2, we need to show that, again, by the definition of this reduction, we need to show that there exists some way to convert them, F. The conversion is going from a statement like this to a graph like this. Okay, so that's our conversion. I'll maybe make that a little bit more explicit here. One sec. So we say if I have some arbitrary SAT formula, so here it's like x1, or I'll just put random things here to make it clear. So this and I have not x1, and then whatever. I think I said x2, not x2, and something else. Let's say x3 also. Okay? So this formula I have now converted to this graph. Okay? So you can imagine the actual, like, what you could be doing in practice here is if I have a SAT problem, someone is saying, I need you to be able to solve these arbitrary SAT problems, and all I know how to do is solve a Hamiltonian cycle problem. I already have a solver for this that exists in the real world, then what could I do? I could take any instance of this, figure out how to transform it into a problem of this type, and then I could solve it. So in this process, being able to do that means that this problem must be harder, because any one of these problems can be solved by a solver that can solve this problem. So what we're trying to do, what a reduction is doing, is taking the entire space of possible problems for this problem, and it's showing how to convert it or reduce it to some subset of problems for this problem. Yes? Yes.
To like 4 more ways to get to C1.
So yeah, there could be as many ways as they show up, right? So as many ways as they show up here, and if you're asking how many nodes are here, you can choose it. Yeah, so you can choose that just by the number of clauses that that variable appears in, either the positive or the negative side, or I can just cap it at the number of clauses times 2. Okay. I'm not going to label it as anything, it's just an edge. We don't need to label any of them. I'm labeling them for the sake of showing you what the reduction is doing, but in the actual thing, this is just a graph. It has no labels on any edges, those are not relevant to anything. But I've shown you through this argument that if this is true, then this is true. Then this is satisfiable. Yeah?
And so we're not looking to find a path where we go forward and we how does the graph ensure that no is repeated?
So it doesn't ensure, so the graph, right, so if you're asking the question, why isn't anything repeated, right, it isn't that there is some algorithm that's running on this graph, it's just, does there exist some way? And we're assuming that I have some way to figure out if there is or not. So if I do this, we can just assume that no solver will ever repeat a node, and we can show that if it's possible to solve that, it's possible to solve this, right? Then there exists a path or a cycle that does not revisit any nodes. And the way that it will work is if I choose x1 to be true, it'll go through here, and then it will choose any clause that it sees that it's able to go to. It won't go to ones that are backwards like this, and then it'll continue and it'll go. And then if eventually, hopefully, C1, if it is satisfiable, there will be some path to C1 that is on the same branch that we've chosen for that assignment of that variable. That make sense? Okay. So again, to overarching here, we have an arbitrary instance of a SAT problem. I'm going to remove this edge. It's there. That goes from the very end back up to S, but we don't need to worry about it so much. It will just make it a cycle. We're taking some arbitrary input, so we say for any possible instance of 3SAT, we want to convert it to a graph such that if this is satisfiable, if and only if this is satisfiable, this will have a Hamiltonian path, or Hamiltonian cycle, sorry. Hamiltonian cycle. And we just constructed a graph that has that property, that will only contain a Hamiltonian cycle if this was a satisfiable original circuit. Okay? Do you understand the point of the reduction? It's not that we need to find out how to find a Hamiltonian cycle, we just need to show that it is reducible to the problem of Hamiltonian cycle by finding a specific case of Hamiltonian cycle that is equivalent. Okay? Yes?
So basically you're saying that
So every instance of, I'll write out the 2 conditions that we care about here. So 2 conditions are that if I have, for every instance of 3SAT, for every instance, we have that if it is true, that is, if the original statement is satisfiable, then my Hamiltonian cycle, I'll just call it HC here, will be true for my converted graph. So I'm using this function f to convert from here to this graph, and I'm saying if the original equation was satisfiable, then there must exist a Hamiltonian cycle. That makes sense? And I also have to show the reverse. I have to show for every one of these, if there is a Hamiltonian cycle for this problem, that means that it was satisfiable. Okay. You understand? So I have to prove both of those things. The construction is designed such that these things are provable. They are true. Right? There's also one other thing I need to prove. Anyone want to tell me what it is? Yeah.
Conversions.
Exactly. I also need to prove that f is in P. So let's go through these. Let me check the time. I do have full proofs of them. Maybe I'll post them if I don't have enough time. We have 10 minutes, so hopefully we have enough. So let's talk about the proofs. So first off, if it is satisfiable, then there exists a Hamiltonian cycle. How could we reason this out? Imagine this is a satisfiable CNF. Then how could I say that the thing that I have now created, this monstrosity, does contain a Hamiltonian cycle? How could I make that argument? And because of time, I'm not going to be super formal with this, but it is relatively easy to make it formal. Yeah.
I guess like because you can take always take one of those all the way down until you get to the
Yeah. So I think what your argument here is take the satisfying assignment. So say assume we have the satisfying assignment to this, which we don't need to actually find it for a proof. We can just say assume that we have it because we know it exists. It exists. So we can say we have it. And if I just go through and I choose for all of the satisfying assignments, I choose which one it assigns. So if it's true, I choose this side. If it's false, I choose this side. This is why I labeled them. If I didn't label them, then I'd have to point out what they are. But I can choose one of them. And then when I go through, as I reach these, I will always go to a clause if I haven't seen it before, and I'll continue. And we'll notice that by doing this, I must be able to visit every clause, because each clause we've reasoned out. We need to be slightly more formal in a full proof here. We've reasoned out the fact that if I am traveling to the left, I am able to visit this clause and continue. And only if I'm traveling from left to right. So only if I take this path am I able to visit these nodes. If I take this path, I'm able to visit these nodes that have the reverse connection. Okay, so we've reasoned that out already, so that can be a piece, like a lemma of our proof. And then we can say, then from that, we will be able to visit each one of these nodes, each one of these clause nodes, as long as it has one of the choices from our satisfying assignment, which by the definition of a satisfying assignment, it must. Every one of the clauses must have at least one of these from each of the clauses, right? Or from the satisfying assignment, sorry. Each clause must have one term from the satisfying assignment. Okay? That makes sense? So this is the, yeah?
Wait, so
Exactly. We'll get there in a second. We'll get there in a second. Yeah. So that is so far that is a fairly abstract proof, but I will say so. The original, like the way you can go about proving it, prove the lemma that you're only able to visit these clauses if and only if you are going in the same direction as them. That is, you go if it is the entrance is to the left and the exit to the right, then you have to be coming from the left to the right. And if you are coming from left and right, you can visit them. Without disrupting the Hamiltonian cycle. So if you prove that as a lemma, then you can say that if I have a satisfying assignment here, then I can just choose that, and I know that I'll be able to visit every clause because of the way I've defined my construction. If it has these true assignment, right, then I must be able to visit this clause, therefore every clause must be visitable, and if every clause is visitable, then there must exist a Hamiltonian cycle. Because every other node I'm going to visit. That's fine, I'm going to visit every other node, it's just whether or not I'll visit these. So as long as all of these are visitable, then I will visit all of them. And then I can say, in fact, that if it's satisfiable, it is a Hamiltonian cycle, this construction, the monstrosity. So this is good. If anyone has any questions on that, you can ask. That was a little bit hand-wavy, but basically the entire proof is what I said. Anyone have any questions on it?
What is
We will get there in a second. Okay, so now the reverse. This is proving that if there exists a Hamiltonian cycle, then we can say that it is satisfiable, or it is satisfiable. The original problem is satisfiable. Anyone want to give an attempt at this? Or maybe I'll give you a minute to think about it. Now you see an example. Let's see if you can come up with a little bit of a proof there. Let me check the time. Okay, we're a little low on time. I think I will actually cut you guys off. So I'm doing this. I can prove it directly, this implication. So I can say, if there exists a Hamiltonian path, that means I visited every clause. And by a very similar argument, I sort of need a reverse lemma from the thing I said previously. If I'm able to visit a clause, then I know that I've chosen each one of these. Either I've taken the left path or the right path for every one of these variable segments. And I can say that that is my satisfying assignment, and I can sort of reverse engineer the same way I did before and say, if I chose this, then I visited every clause that did this, and that assignment of them must be a satisfying assignment. So I know that it exists because my choices, either left or right from each one of these middle nodes, will be a satisfying assignment to the problem. I can build off of my previous lemma to prove that. Does the outline of that make sense at least? I want to make sure that people understand broadly what I'm saying. I'm not being tremendously formal because we're low on time, though. Okay. And lastly, one of the more interesting parts of this problem is F in P. So, it's something you can't forget about, because it's very easy to show reductions if you don't have this constraint. It's very easy to reduce anything to anything. So, how do we prove that this is polynomial time to construct this graph? Any ideas? Yeah. Exactly. We have to show that the amount of nodes and edges scales polynomially. I guess vertices is probably, no, it won't, because it'd be, whatever the case, show the number of vertices and edges scales polynomially with this number of clauses. And what we notice is, as was said here earlier, the number of these that we need per layer is at most 2 times n plus 2 for the 2 n pieces. That's per clause. N is our clauses normally. And then we also need one of those. We need one of these chains per variable. And at most, there are 3 n variables, because n is the number of clauses. At most, we have individual variables for every clause, or unique variables for every clause. So this is going to be 2 plus this, I suppose, is going to be, for a certain n, is going to be the number that we need. I guess it'll be plus n, actually, but it's fine. And all of this, we can say, is definitely going to be O of n squared, which is clearly in P. So this is going to be in P, and that's fine. And so we have now proven that Hamiltonian cycle is in NP complete. Yes?
Can I make an announcement?
One last thing first. Last thing I want all of you to consider, this is going to be a simpler reduction. Hopefully someone can say it very briefly. There's a separate problem called Hamiltonian path. Hamiltonian path is the same. You must visit every node exactly once, except it is not a cycle. It doesn't repeat any node at all. How can we do a reduction from this to that? Yeah. Basically. So it'll require a little bit more work than that. You can think about, if I'm given a Hamiltonian cycle problem, I can't actually solve for what the Hamiltonian cycle is. So you have to consider that as part of your problem. Okay? Okay.
Wait, did you mean reduce ham cycle?
Yes, exactly. Yeah, ham cycle to ham path. Ham path is the more common problem they run into. Hamiltonian path is a very common thing. That's why I misspoke a few times. Hamiltonian cycle is just another problem that we can then reduce from. Okay. I'm going to leave that as a little hanging question for you. If you're interested, you can talk to me about it, but it's a relatively easy proof. And lastly, we have an announcement for our SI about SI sessions, which if any of this was complicated to you, you should attend. Tomas seems very knowledgeable on this.
Yeah, if any of you are like, well, there wasn't a discussion last Friday also, so if anyone's like, oh, this is really abstract stuff, I want to have good review for it. My review sessions are on Tuesday and Thursdays. I'll send an email just to remind everyone of the times and the place. And this is like my 6th time learning about complexity here in UMass, so I hope I got this.
like nodes in every line. Like, I know there's like a number.